This video continues to focus on linear and nonlinear functions. Specifically, we tried to determine if a table is a linear function or not. Tables may be more challenging than graphs and equations to tell if they're linear functions, but again, we start with the definition of what a linear function is. That means any function that graphs to a straight line. We should recognize that the straight line is the result of a constant rate of change, or a slope that stays the same. Because of that, we're going to focus on these tables on figuring out, do they have a constant rate of change? Are they really going to make a linear function? Or when we graph it, would it be a nonlinear function? We see two examples here where they ask us to determine whether either of these tables represent a linear function. And there are two good methods we could use to try to determine if tables are linear or nonlinear. The first method is just to turn them into a graph. That will take a little bit of time, a bit of work, but we already know how to tell if graphs are linear or not. We just look to see if they're a straight line. So I could go ahead and graph each row or each ordered pair that's listed in the table. Each of these solutions can get plotted onto a graph. So the first point, 0 and -6, I start at the origin. If x is 0, I don't go left or right at all. If y is -6, I go down 6. That's the first solution in our green table. When x is 0, y has to be -6. Next up is 2 and 0. So I start at the origin. X is 2, I move 2 to the right. Y is 0. I don't have to go up or down at all. 5 and 9. We again start at the origin, move 5 to the right, move 9 units up. And the last one, 6 and 12. We move 6 units to the right, 12 units up, which is a little above on our graph, but we can see if we go about at 12, all 4 of these fall on a straight line. We could say that because of this, we already should know function g is going to be a linear relationship. We do the same for the table r, or the function r, to figure out if it's a linear relationship. The first point, -4 and 6, I go 4 to the left, 6 units up. That's our first point. -2 and 7, we would go 2 units to the left, 7 units up. 0 and 8, that's our y-intercept, right at 0 and 8. And as of now, it looks like a linear relationship, but when we plot this final point, 2 for x and 7 for y, we see our function has changed its mind. It's now changing its slope and heading down as x is getting larger. So that must be some type of nonlinear relationship. By plotting these points on a graph, I can see the green table, function g, would be a linear relationship. Its graph is a straight line. Function r is not linear. Graph changes direction. Instead of graphing, which does take a little bit of time, but if you have a whiteboard handy with a graph on it, or you have graphing paper, or even a graph available to you on a computer, this is not that bad of a method. But a quicker and easier way is just to try to measure and see, will the slope be staying constant? Does the table follow a constant rate of change? And if so, we know it would be linear. We'll show an example. For the green table, we see from the first row to the second row that x goes from 0 to 2. That's an increase of 2 units. And we see during that same time that y goes from -6 to 0. That's also an increase to go from -6 to 0. We've gone up 6. So if we talk about the slope from row 1 to row 2, the y goes up by 6 as the x goes up by 2. Similarly, at the next row, from row 2 to row 3, the x goes from 2 to 5. That's an increase of +3 units. And during that time, the y goes from 0 to 9. That's an increase of +9 units. The x goes from 5 to 6 from the last 2 rows. That's an increase of +1 unit. And during that time, the y goes from 9 to 12. That's an increase of +3 units. If we put that as a slope from the last rows in pink, y goes up by 3 as x goes up by 1. And if we look at this middle row, y went up by 9. And during that time, x went up by 3. We see something. 6 divided by 2, that equals 3 over 1. 9 divided by 3, that equals 3 over 1. Because we see a constant ratio here, a constant slope or a constant rate of change, That's another reason that we know function g is linear, because the slope stays the same. If we went and did this for the red table, we would certainly see, because of what we see, this change of direction, at some point the slope would not be the same in that table.